Alrighty. Good morning, everybody. Howdy. Thank y'all for being here. Hope y'all are all doing great. Um, let's see. Gonna start y'all out with a quick quiz. So if y'all wouldn't mind clearing the stuff off of your desks, all you're gonna need for the quiz is something to write with. Toss these out. Keep them face down until everybody's got one, please. Did you just give me a copy? Okay. Oh, sorry, I didn't realize this had already started. Everybody's got one. All right, y'all are good to flip it over and get started. Good luck. Let me know if you have any questions. On that first one, if the wording is confusing, you're basically drawing three plots. You're plotting phi1, phi2, and phi3. Uh, they should show the main kind of trends, but they don't have to be like perfectly illustrated. About one more minute. Alrighty. That was the end of time. If y'all would please put pencils down. Make sure you got your name on it, but otherwise pencils down and pass those up, please. Got everybody's? Alright. Hopefully that one went okay. Thank you for indulging on that. Just real quick, there's no class on Friday, so there's also not going to be there's no help there, it's a holiday on Friday, so no help session. My girlfriend made some little bars that have like caramel and chocolate, and it's kind of like a cookie thing on the bottom. So if you guys want to all come up and grab one if you want, there's napkins and for some reason, please, if you want one, feel free to come up and grab one. I just have to make an adjustment to my slides because for some reason the version I was going to show y'all got corrupted. So I'm having to just like add the blanks real quick. So we'll just take a quick little snack break while I figure out my slides and then we'll get started.
So just grab one.
Yeah, just grab one. And then after everybody's had one, if you like it, feel free to take more.
First one's the hardest one. Save this for bottom. Do it. Thank you.
Will do. You're welcome.
No, I just.
Oh, thank
And then
you.
there's this one that I think got mixed up in that pile.
Gotcha. Thank you. And then I guess while I'm also fixing these slides real quick, um how's homework 4 going? Uh homework 4 was originally supposed to be due. Does anybody have questions on homework 4? That one was originally supposed to be on Tuesday, but we had the thing with class being canceled on Tuesday, which I didn't realize. So sorry that I didn't include that information earlier. But yeah, so hopefully it was okay to just extend that homework by 2 days. If we have questions on it still, this would probably be a good time to answer those. And I just have a few more blanks that I'm fixing. I apologize. Usually what I do is I make the full presentation and then I add the blanks, but when I added the blanks this time, the file just kind of corrupted and didn't save anything that I thought I saved, so I'm just adding a few more, and then we can get started. So I guess I could just talk about housekeeping stuff while I'm doing this. So because of the no class on Tuesday, our homeworks are gonna kind of be shifted around for the next two. So like today is Thursday, and I'm gonna be assigning homework 5. So that means I'm gonna give you a week for it. So that means that homework 5 is gonna be due next Thursday. Um, and then if you're keeping up with the schedule, we're gonna have our exam 2 the week after. So not this Thursday, but next Thursday. I believe on the calendar that's let's see, this Thursday is the 8th. So yeah, no, sorry, this I can't read. Yeah, yeah, 10th and then 17th. Yes, exactly. Exam 2 is coming up. I'm gonna try to have you guys get you exam 1 back next week. And but so in terms of like not having the feedback from that, I do apologize that you haven't gotten exam 1 back yet. If you're like wondering about the feedback though, basically it's all homework 1, right? Like if you look at the questions that we had on exam 1, it's basically just the homework. And you got feedback on the homework, assuming that you're turning in the homework. If you're not turning in the homework, that's a different conversation that we should have. Um, but yeah, so that'll basically be the plan. And then next Thursday, and it's just the unfortunate thing because of how the timing worked out, that next Thursday is going to be the start of a new homework 6, but then the following Thursday is going to be the exam. So unfortunately, it is going to be another situation where the homework is going to be due on the same day that you have the exam. Um, if it is helpful, like if we know that we're gonna procrastinate, I can make it due the day before, or I can make it due like at 8 a.m. if you feel like, because I normally what I would do is I would set the homework to be due Thursday at midnight. But if you're a procrastinator, then you're not, and you don't do the homework before you take the exam, there's going to be a big section of that exam that you're not going to do as well on if you didn't do the associated homework problems. So if you want, I can make it due a day earlier, or we can just make sure that we are staying on top of our stuff and getting that homework done before we take the exam, with the understanding that we want to do the homework first so that we have confidence in the material, so that when we see similar style problems on the exam, it's not a surprise. And we've already practiced those things, right? That's the whole point of the homework, is to get us practice. So that would be my advice. If you did procrastinate on homework 3, it probably hurt you on exam 1, and it'll be a similar thing with homework 6 and exam 2. So hopefully that makes sense. Again, sorry for the delayed. I guess maybe it's fitting that my presentation was delayed, because today we're going to be talking about delayed neutrons, and we're also going to be talking about the reactor design. Um, Thank you all for question.
So with kind of exam 1 having been mostly questions similar to homework 3, so it's gonna be the same kind of theme with the next exam, how it's from homework 6 maybe? Or
Well,
at least similar concepts.
What I feel is that the homework builds on itself. So like the derivation that you got was based on homework 3, but most of the calculations were actually based on earlier homeworks. So in general, your exam 2 is going to cover homeworks 4, 5, and 6. So if you know how to do the problems in 4, 5, and 6, you're going to know every problem that you see on the exam, because you're going to already have practiced everything that I could ask you. I wouldn't say just focus on homework 6, because then you could end up, missing things that are also going to be important. Um, so the last time that we were here, we were talking about like heterogeneous versus homogeneous configurations, and we were just starting to talk about if you have like a full reactor core, like this is a reactor core map for a light water reactor. So every square is an assembly. The way that these assemblies are usually set up in a reactor core is that you have like fresh fuel on the outside, and that's fuel that like you've just put into the reactor. And then as you go radially towards the center, you have fuel assemblies that have been in the reactor core for longer. So it's like fresh fuel on the outside and more irradiated fuel on the inside. If you have more irradiated fuel on the inside, it means that it helps flatten out the flux profile to have fresh fuel on the outside and then more used up fuel on the inside. So this is like what a reactor core looks like. And when we homogenize, we're going to assume that this reactor core can be represented as a basically an infinite array of fuel and moderator cells. So this is what we are saying is the assumption is that we're going from our full reactor core to assuming that we have an infinite array of fuel and moderator cells. In this conversion process, we're going to assume that the number of cells, right? Each of these, there's basically a cell associated with each region around a fuel pin in our infinite lattice. And what we're going to assume is that if we were to take the volume of our full reactor core and we divide it by the volume of a single cell, that basically what we're saying is that the number of cells in our reactor evenly divide into the reactor's volume. So that like if the reactor core has a volume of 1 meter cube and we have 100 cells, then we're assuming that each cell has the same volume and that all of those cells fit evenly into their volume without any like leftover pieces of the volume. So this is what a square infinite assembly, infinite array of fuel moderator cells would look like. The reason that we set it up this way is that these assemblies are square packed, so our fuel moderator cells end up being square packed too. And if we wanted to isolate a single cell, you could draw these dashed lines anywhere around. And basically what we're just saying is that we kind of have the same amount of space kind of separating every single cell. That's what this dashed box is supposed to represent. It's supposed to represent the boundary of our cell. And when we're looking at an infinite array, we're choosing that cell boundary such that we can basically break up our infinite array into a bunch of little pieces. So if it's a square assembly, square arrays, then your unit cell ends up being a square. And so if I go to the next slide, this is what that cell looks like if I were to zoom in on the cell itself. And we have an infinite array of these fuel and moderator cells, infinite in each direction. So if we were to ask about like the profile around a single cell, if we were to ask like what does the temperature profile look like, or what does the flux profile look like, how would those profiles compare from cell to cell if we have an infinite array of these cells? They're all going to be the same, right? If it's an infinite array, then these profiles around each cell is going to be identical. So if it's an infinite array and every cell is the same, we can just look at a single cell, do our analysis for a single cell, and then that cell will be like representative of any individual cell in our system. So if this is our cell, we're kind of treating this as our reactor, and we're going to homogenize over this cell. So basically what we want is we want a reaction cross-section for the whole cell. And if this cell is made of materials of different regions, right? Like we have a fuel region in the middle, we have a cladding region that surrounds the fuel, and then we have a coolant or moderator region. The cross section for this cell, you might think that it's just like a simple volumetric average of these regions. So like what I'm trying to say is that we're going to have a cross section for the fuel. So the fuel region, and this could be any cross section, right? This could be a fission cross section. It could be a absorption cross section. X is just representing any kind of reaction. And then this is G for the energy group. And so we're saying we're going to have a cross section for the fuel. And what we're going to do to average over the cell, you might say, we're going to just multiply this cross section for the fuel by the ratio of the fuel volume to the cell volume. So if we take this and then multiply by the volume of the fuel divided by the volume of our cell, then this term is like the volume weighted fuel cross section. And we would volume weight the other regions as well. So like if there's also a cladding region, so we're also going to have a type X cross section for group G for the cladding. And if we're doing volumetric averaging, then this would also be multiplied by the volume of the clad divided by the volume of the cell. And we would do this for every material that's in our reactor. So we have coolant or moderator as well. So we would also have a cross section of type X for group G for the moderator. And then to get that, we would multiply it by its volume fraction, which would be the volume of the moderator divided by the volume of the cell. So this might be how you would think that we would average the cross sections over a cell. Is just take the cross section for each region and then multiply by a volume fraction for each region. In this case, sigma xg for the cell represents the volume average type X cross section. So it could be a fission cross section, an absorption cross section, a scattering cross section for some energy group G for the entire cell. So when we write cell here, this is averaged over the entire cell. This is still just a cross section though. So if it's a cross section, what kind of units should it have? Inverse centimeters, right? 1/centimeters. So its units, it's still a cross section. It still has those same cross section units of inverse centimeters. So this is how you would do simple volumetric averaging of your cross sections in your cell. And if that's okay, then we can start defining what the parameters in that cell are going to look like, what the volumes of the cells are going to be. And to do that, we just have to define some terms. So one of the things that this cell has depth. So I'm drawing a little an X here to say that H is the depth that we go into the page. Um, like if this was a real reactor core, these cells would all have a height that is the height of the reactor core. So there's some vertical height into the page. If you look at design control documents for a reactor, they'll give you information like the fuel pen radius, the cladding thickness. So if you know some of these things, we can start computing the domain, like the volumes of each region. So if our fuel is if our fuel is the radius of the fuel, and then our clad is the radius of the outer cladding region, if this is the cladding radius and this is the fuel radius, what would I do to get the little thickness of the cladding right here? Subtract the radii, right? It would be like R clad minus R fuel would give me the cladding thickness. R of the clad minus R of the fuel would give me that thickness. And the unit cell also has a width. Whenever we made this unit cell, we were basically trying to draw a cell that kind of isolated our individual cell from all of the others in in a uniform way. So if I just go back real quick, notice that this distance from here to here, that distance from like the center of one cell to the center of another cell, that has a name. That distance has a name and it's called the pitch. And we use the symbol P for the pitch. And if I draw my unit cells in such this way that they are cell centered, what it means is that the width of my cell is the same as the cell pitch. So if I were to go back to my picture of my cell and I were to talk about the width of the cell, that is equivalent to the pitch for this configuration. So we use a symbol P for the pitch. It's a distance. It has units of centimeters, and it just represents how wide this unit cell is. It's just the thickness or the width of that cell is how we define the pitch. So if we have these geometry things defined, if we know the pitch, and if we know those two radii, then we can actually compute all of the volumes of these regions and the volume of the cell itself. So like the cell is a square cross section with a height h. So what's the what's the volume of my whole cell going to be? Yeah, and it's a square cell, so the length and the width are both p. So we got a p squared, and then times the height, right? So the volume of the cell, perfect, is going to be p squared h. Yeah, it is the volume. So it's pitch, the area times the height. And then if we want the volume of the fuel pen, this fuel pen, it's a circular cross section, but it has height, so it's really a cylinder. So what's going to be the volume of that fuel pen? Just in terms of the fuel radius. Perfect. Yeah, pi times the R of the fuel, right? R fuel squared H, right? Area of that little circle of the fuel times its height into the page. How about the cladding? How do we get the volume of the cladding? Well, but be careful though, because if you do R clad, you're pi R squared for the clad minus pi R squared for the fuel, right?
R clad max R.
So technically, this is going to be the volume of the clad sphere, or sorry, clad cylinder minus the volume of the fuel cylinder. And so clad cylinder is going to be pi R clad squared H. Volume for the fuel is going to be pi R fuel squared H. So the pi and the H are like a common factor that you could factor out. And then what you're going to have there is a difference of the radii squared, right?
So it's pi R clad R squared.
Yeah, that's the other way that, yeah, exactly. Yeah, R clad squared minus R fuel squared times H. Sorry if that's a little small, but yeah, it's pi times H times the difference of those radii squared. And now we have the volume of the whole volume, the cell, and then the volume of the fuel and the volume of the clad. So how could we use all of those pieces to get the volume of the moderator? Mhm. Right, the moderator is just going to be the cell minus the other regions, right? So I'm going to have the volume of my cell minus the volume of my fuel minus the volume of my clad. So you would get the fuel radii and the fuel and the cladding thickness and the pitch from like a design control document. You would get the height from a design control document, and then you can compute these volumes. And then once you know the volumes, you can also compute the volume fractions by just taking ratios. And like if you are doing calculations that just require you need the ratios, then the height doesn't really matter because you're going to end up dividing the height out when you take a ratio anyway. But if you're doing these calculations to get an actual volume, it's best to use the height, which is the reactor height. So if you always use the reactor height, your calculations will never be wrong. But if you don't have a height and you're just doing fractions, you can just assume a unit height of 1 and it'll all work out to give you the right volume fractions. So if the problem with the approach that we introduced where we're doing volumetric averaging is that it ignores something really important, which is that especially if you have a thermal reactor, your flux is going to vary considerably from region to region. So it fails to account for regional variations. Regional variations in your energy dependent flux. So as phi as a function of R and E. Um, and think about that, right? In the fuel, we have very different cross sections than we have in the moderator. And the moderator specifically is like a very high scattering cross section. So the moderator is going to result in our neutrons losing a lot of energy when they pass through the moderator. And as a result of that, we get those regional differences, and basically the flux changes a lot when you go from the fuel to the moderator. So as a result of that, the way that we handle it is that we introduce something called the group flux disadvantage factor. And we use the symbol zeta for the group flux disadvantage factor. And basically all this is it's a ratio of the flux in one cell. So it's the flux in cell in region I for group G divided by the overall flux for group G in the entire cell. So I, in this case, I is just an index for my region, right? So I could be a fuel, it could be a clad, or it could be a moderator. And then I'd have a group flux disadvantage factor for the fuel, for the clad, for the moderator, what that disadvantage factor would look like is just the ratio of my flux in that region divided by the flux in the entire cell. So the more proper way to do a volumetric average of a cross-section is to both multiply by the volume fraction, but also to multiply by the flux disadvantage factor, which will basically help account for how much of the overall flux is associated with each region. Right? That's what we're doing with the volume fraction. We're just saying how much of this total cross-section for my cell is going to be based on the cross-sections for each region. And if like my cell is mostly fuel, then V fuel over V cell will be about 1, and all of those other fractions will be about 0. So like most of the contribution would be coming from the fuel if your cell is mostly fuel. That flux disadvantage factor just adds another piece onto that, which helps you account for how much of the flux is in each region. Right? How much material is in each region, that's the volume fractions. How much flux is in each region is the flux disadvantage factor. And accounting for both of those would be like the more appropriate way to do cross-section averaging or cell homogenizing. So that's what the equation looks like. And in principle, if we were to get these cross sections for the whole cell, then we would basically know a overall cross section for the group. And if we had an overall cross section for the group and we wanted to start finding like K effective or like the group flux components, we could start doing that by just doing like multi-group diffusion, like doing the zero-dimensional model that we were seeing in homework 4. So basically, once we do this volumetric averaging, we can then do multi-group diffusion. We can do multi-group diffusion kind of just like we were doing in homework 4. And that multi-group diffusion, it's basically going to help us get an energy distribution in our cell. And then it would also tell us about K effective as well. So that would be the approach. And if we could do that, we'd be able to get K effective and know the energy distribution in our cell. Do we see any issues with trying to use this approach to find those flux components? Because that's what multi-group diffusion will give us, right? It'll basically give us like the group averaged components. But if we want to do this like complete cell averaging where we also know the flux disadvantage factors, knowing the flux disadvantage to use the flux disadvantage factor, you have to know the flux in each region, right? And we don't know that yet. So that's kind of the hard thing with this approach is that you need phi, you need the flux to find your disadvantage factors, your zetas. So in a real reactor problem, you're basically going to have to you're going to use a computer to solve it, and that's how you're going to get all of your group flux disadvantage factors. But if we can't do that, we need a way to proceed that will allow us to do like some analytical calculations. And so that's what I was going to focus on is how we can kind of get away from needing these flux group disadvantage factors in the first place. So these are our flux group disadvantage factors. They are there because you have regional variations in your flux from region to region. So if you think about like a thermal reactor versus a fast reactor, we already talked about how a thermal reactor has to be treated as a heterogeneous system, but a fast reactor can be treated as a homogeneous system. We can think about that based on what we talked about last time in terms of the mean free paths of homogeneous versus heterogeneous configurations. And basically fast reactors have a very large mean free path. Thermal reactors have a small mean free path. As a result of that, you can homogenize a fast reactor core doing simple volume averaging. What it basically means is that the flux is not going to vary very much from region to region if you have a fast reactor compared to how much the flux will vary from region to region if you have a thermal reactor. So in the fast reactor, you can treat it as homogeneous, and the flux doesn't vary much from region to region, which means all of those flux disadvantage factors, if there's very little variation in my flux from region to region, I can ignore those flux disadvantage factors. If it changes a lot, the flux changes a lot from region to region, I can't ignore them. So for the thermal reactor, the flux does change from region to region, and this disadvantage factor is not something we can ignore. we can not we cannot ignore the disadvantage factors in the thermal reactor, but in the fast reactor, the moderator is there isn't a moderator, it's just a coolant. That coolant is usually very neutron transparent, so neutrons don't really interact with the coolant much in a fast reactor. That means that the flux doesn't vary much from region to region, and that means that in so if the flux isn't changing very much from region to region, if the phi for my region is pretty close to the phi of my cell, what does that mean about the value of my flux disadvantage factor? If these two quantities are pretty similar, what's this number going to be? It's going to be 1, right? It's going to be very close to 1. It's going to be approximately 1 if the flux in my, say, the flux in my moderator divided by the flux of my cell. If the flux in the moderator and the flux in the cell are similar, then that ratio is going to be about 1. And similar for the other regions, if the flux doesn't change very much, then those flux disadvantage factors are going to be about 1. Therefore, we can basically just get away with that simple volumetric averaging, because if we go to our more detailed formula, all of these flux disadvantage factors are going to be 1 for a fast reactor, and then we don't have to worry about needing those disadvantage factors, and we can just do simple cross-section homogenization for a fast reactor, and we're in luck because our reactor design problem is for a fast reactor. So this is kind of helping us get set up and to understand and know how to approach the reactor design problem. That one is going to be due August 5th. It's already available, and after today, we'll have everything we need to fully do that problem. So my advice would be to get started on the reactor design problem sooner rather than later. Just because like it's just a homework grade, like it's a long homework. I wouldn't think about it as anything more than that. So, to the extent that it's going to take time, it might take a little longer than a normal homework, but you shouldn't have to spend that my I wouldn't spend that much more time on it because it is just a homework grade. But don't wait until the last minute, because if you wait, then it's going to be harder to get help. So I posted this on Canvas and on Google Drive. The reactor type is a sodium-cooled fast microreactor. Um, Fast reactors aren't really used or explored that much in the US, but abroad they are. In total, about 20 of these fast reactors have been built. Most of them are in Russia. So 400 reactor years, it's like if you were to take all of these fast reactors and add up how long all of them have been operating, it's about 400 reactor years of operation. So like these designs have been built, they have been analyzed, they've been understood. And there's a lot of reasons why we will probably want to adopt fast reactors at some point in the future. Whenever you're having conversations with people about nuclear engineering and nuclear power, one of the questions that you probably get asked is like, what do we do with the waste? How about the waste? The waste is such a big problem. And, as a nuclear engineer, part of the way that you can respond to that is you can say, well, we need to build fast reactors, because part of the thing with fast reactors is that in a fast neutron spectrum, you can actually make the actinides in your waste fission. So like, we have the spent fuel. It is dangerous because you have a lot of these actinides in there that are radioactive, but we could just take that spent fuel, put it in a fast reactor, and then burn up all of those actinides and also produce a lot of power in the process. So if you use fast reactors, you can make your waste generate you power. And that also means that you're better utilizing like your uranium resources. In terms of like design, fast reactors don't need a moderator. That makes the core smaller. You could argue that that maybe reduces some of your design cost or complexity. And one of the other cool things about fast reactors is that you can make them set up so that they make more fuel than they consume. And that's the whole idea behind breeder reactors, and specifically fast breeder reactors are the kind of reactor that can do that. Question?
So what's the, why did
I don't really know. That's one of those questions that like it's almost as much of a political question as it is an engineering question. And part of my understanding of like why we've pursued the technologies and the fuel cycles that we've pursued is that it like is well aligned with our objectives in terms of like weapons and things like that. I don't know if that's actually the reason. That's like kind of part of what I would probably assume, is that like ultimately nuclear is in this weird space where like it is a power thing, but it's also very much like a national security thing. And so people end up making design decisions for a variety of reasons that aren't just economics. And I guess part of it is that all of these things, it is a different approach to what we do. Like our fuel cycle is a open fuel cycle, so we don't reprocess. We just put fuel in a reactor, let it burn, and then once the fuel's been in the reactor for a couple of years, we take it out and it just sits in like a dry cask. So we have decided that approach for a variety of reasons. Different countries might have different priorities. They might have different concerns about materials, like how much fuel do they have, in which case maybe they decide to go like closed fuel cycle. It's a more complicated to answer in a kind of hand wavy way. It's kind of more complicated than just like the economics or just the technology. So we're going to do the same cross-section homogenizing that we talked about for the square assembly with our fast reactor. And in a fast reactor, they have hexagonal assemblies. So this is like what the assembly map of a fast reactor would look like. And it's a similar style setup where like you have inner fuel assemblies and you have outer fuel assemblies. The outer fuel assemblies are going to probably be higher enriched than the inner fuel assemblies. Um, if you look at this as an infinite array of fuel elements, fuel moderator, fuel coolant elements. Now, if we had hexagonal assemblies, we end up, this is also with a triangle, this is called a triangular lattice. So instead of our fuel pens being right next to each other, they're oriented in this little triangular arrangement. That means that the way to isolate one cell from the infinite array is to make your cells be hexagonal and not be square. So the reason that our cells are hexagonal for the fast reactor is because we have triangular assemblies, which result in triangular lattices, which result in hexagonal unit cells. So it's like a very similar approach. Your cell just has a different outside geometry. But there is a formula. This is the formula that you could use to calculate the volume of a hexagonal cell. And that square root 3/2 just comes from doing trigonometry. Like you could derive this if you wanted. It comes from the fact that in a hexagon, each of these triangles, there's 6 of them. And so if you do 36 divided by 6, you get 60 degrees. So you're going to have like some signs of 60 degrees in your calculations flying around, and that's where that 3/2 comes from. But anyway, so what you are basically going to do is just we can ignore flux disadvantage factors because it's a fast reactor. So we can get the cross sections for our cells by just doing simple volumetric averaging. And why is it that we can neglect the flux disadvantage factors for the fast reactor? Yeah, there's little flux variation, right? So little variation in our energy dependent flux. So we already hopefully can see that I'm going to give you information with like radii and thicknesses in the pitch. And so you'll have everything that you need to calculate these cell volumes and cell fractions. Um, and so this is part of a table that's given to you in the design in the problem assignment document. So like the fuel here is going to be a uranium metal mixture. That means it's going to be some uranium-235 and some uranium-238. So if I want to get my cross sections for the fuel mixture, I'm going to have to do something with the cross sections of 235 and the cross sections for 238. How would I do that? Like if my fuel is made of 235 and 238, what's my cross section for the fuel gonna look like? How did we define big sigma in terms of like a little sigma and a number density? Yeah, right. It's going to be the number density times little sigma. And this was if we just had one material, like one material. But if we had two different materials, um, what how does this become different? Well, Yeah, there's two different materials, so it's like our total cross section. Do you all remember at the very beginning when we looked at like the box and we had some atoms of type X and some atoms of type Y, and we asked about like how does the interaction rate with just X, like there's going to be an interaction rate with just X, there's going to be an interaction rate with just Y. The X and the Y's don't really interfere with each other. So that means that if you have a mixture, you just basically add the cross sections for the individual components of the mixture. So if we have 235 and 238, then we're going to have a sigma X for group G for 235 times the number density of 235, plus we're going to have the sigma X for group G for uranium 238 times the number density of 238. Right? And so the micro cross sections are given to you. The atom density is something that we can compute. How do I compute the atom density? What was my formula for atom density? If I just wanted atom density of some material, how did I calculate that? What was the formula for that? Perfect. Yeah, the mass density times Avogadro's number divided by big M, or you could say big A, it's like the atomic mass. And that was just for one kind of component. If I have multiple components in my mixture, all I have to do is basically multiply by the atom fraction. And that's what X is. So in this problem, we are going to assume that there's some enrichment of the uranium-235, and that's what X is, such that overall the fuel metal, it's going to be my fraction of U-235 times the amount of 235, plus my fraction of U-238 times the amount of 238. So these calculations, like for 238, it's going to look just like this, but I have to include a multiplier of 1 minus X up front, which is basically the fraction of the overall uranium atoms that are type 238. But that's going to be the density of the fuel times Avogadro's number divided by the atomic mass of 238. And what's the atomic mass of 238? 238 grams per mole, right? And density of the fuel is the density of the fuel mixture, which is that 17 grams, grams per meter cubed, grams per centimeter cubed, sorry. So similarly, the number density for uranium-235 is just the fraction of U-235 atoms that are there times the fuel density, which is the similar thing over here, but we're dividing by the atom, the molar mass of this component. And if it's uranium-235, then we're dividing by 235 grams per mole. So that's so notice you're gonna have to set the enrichment. That's gonna affect your number densities. Your number densities are gonna affect your cross sections, and your cross sections are gonna end up affecting what your group flux components look like and what your K effective looks like. So you actually only have one knob that you're adjusting. It's the enrichment. So you're basically just gonna set the enrichment to be a variable. You're going to have a code or an Excel spreadsheet that does these calculations. And you basically want to be able to change the enrichment, have it do all the calculations to ultimately see like what the resulting K effective is. So we are going to make some assumptions. We're basically going to be using that zero-dimensional model that we saw in homework 4. That's the thing where basically once you know all of your cross sections and your group fission, like your group spectrum components, then you can do some relatively straightforward calculations to get your group flux components and your K effective. There's no reflector. The metal is stainless steel, but we're gonna assume that we can just use iron as the material that represents stainless steel. And then you're given these 8 group cross sections that are already properly averaged, the micro cross sections for each group. So ultimately, what your objective is to use those assumptions and the given information to design a reactor core that has this K effective, plus or minus 0.01. In the document, I explain everything that I want from the report, from it, what you should be delivering, the deliverables, as it were. And basically, it's going to be like a short report and then responses to the questions that I've asked in that document. Um, So like we were saying, your enrichment is going to affect your cross section. That's going to affect your group components. That's going to affect your K effective. So basically pick a guess for X. Convert all of your micro cross sections to macro cross sections. Like in the table, you have your micro, you multiply by the number density of that material to get the macro cross sections. Once you have the macro cross sections for each region, like for your fuel, for your moderator, and for your cladding, then you can average your cell cross sections to get a like overall cross section for the cell for each type of cross section that you need. And then once you have all of those group average cross sections for each group, you will do your zero-dimensional model calculations, very similar to homework 4. You'll get your group flux components, you'll get your K effective, and then if you set it up using a program like a coding or Excel, then you can just enter X, the enrichment. It'll do all these calculations for you, and then you can see what the resulting K effective is. And then what I would do from there is just adjust X, see what K effective is. You could even eventually you're going to need one of the things you're going to produce is a plot of K effective versus enrichment. So one thing you could do is just change X, see what the resulting values are. That would be the way that you could generate all of the data for that plot. Um, so yeah, and these calculations that you do for the cell. Oh, question?
Look there, we have pointing from James.
No, all the cross sections are given. Um, And so all of these calculations are on a cell basis. So like you're going to have the volume of a cell, you're going to have the volume of the fuel in a cell. If you know the total core volume and you know the volume of an individual cell, you can get the number of cells by just dividing them. And once you know the number of cells, you can multiply by like the volume. If you know the volume of a single cell, like the fuel volume of a single cell times the number of cells, you multiply those two together, and that gives you like the total volume of fuel in your core. You multiply that or use that with the density to get the total mass of fuel in your core. And then you use your enrichment to say, of my total fuel in my core, this is how much is 235 and this is how much is 238. So that was like the general approach and recommendations for the reactor design problem. So hopefully that should give you a good starting point. And basically the first thing that you're going to want to do is just get all of your cell average cross sections. I think what I will probably do is what I'll do in a couple of days is I'll post a table that shows you what the cross sections should be if you set the enrichment to 50%. So that way, in your code, what you would do is you would set enrichment to 50%. You would look at all of your cross sections. And if your cell average cross sections match my cell average cross sections, then you know that all of your underlying calculations are right. And then you could have confidence that you can move forward from there to do the parametric adjustments based on your actually changing the enrichment and seeing what the new K effective is. So that'll be something I'll do just to help you with debugging. And if there's any questions about the project, just let me know as they come. Just hopefully don't wait to the last minute. Because if you do wait till the last minute, I will still try to help you. It just becomes a lot harder if we're time constrained. So getting into the topic for today and getting into basically chapter 6 of the Svetkov notes, we are moving into time dependence and in analyzing time dependence in a more realistic way. At this point, we've already considered a couple different scenarios, right? We've seen bare reactors, we've seen multi-region reactors, we've seen reactors where we have some details about like the energy distribution and group multi energy dependent and multi-group diffusion. So we're going to kind of keep doing that, and we're just going to basically better understand how time dependence factors into what we've studied so far. Because up until this point, we've basically assumed steady state for most reactors that we've seen. So imagine we have a reactor that's critical, that's operating in steady state, and then suddenly a control rod gets ejected out of the core. That removing the control rod from the core is going to change the characteristics of our system. If we remove a control rod from the core, how's that going to affect the absorption rate in our core? If so, the control rods, are they there to absorb neutrons or make neutrons? They're absorbing them, right? So if we take this absorbing material and we take it out of the reactor, how is that going to affect the total amount of absorption in the reactor? Is the absorption going to go up or down if we remove a control rod? It's going to go down, right? We're reducing the amount of absorbing material. So the absorption rate, like the parasitic absorption rate of neutrons in that control rod, the absorption rate is going to go down. And how, if absorption goes down, what is that going to mean about the production rate of neutrons? Like if we compare the gains or the production versus the losses, previously it was critical. So when it was critical, what does that mean about the gains and the losses? They're balanced, right? And now we've removed a control rod, we've reduced the amount of absorption. So now, how does the production rate compare to the loss rate? Is it bigger or smaller than the loss rate? It's bigger, right? So if the production rate is now bigger, we're now at a configuration where we have more production than loss. So what is the reactor configuration if we have more production than loss? Supercritical, right? So this supercritical. So this is kind of an illustration of what you might call a transient. You have like a reactor operating in a steady state. You have some event in the reactor that makes the system deviate from criticality, like you remove a control rod, or there's a lot of different things you could do in a reactor to change its current state. And what we want to be able to understand is when you make a change like this to the system, how does it affect the system? And also, how does the system behave as a function of time after you make that change? That's what we're going to be studying today. And part of that story and understanding time dependence is to talk more about the neutrons that are coming out of fissions and characterizing them according to the time over which they are emitted. So like we saw this picture where it's depicting the fission process from like a neutron hitting a nucleus to that nucleus splitting. And so this picture right here, this is the illustration of the neutrons. The green things are neutrons, and these are the neutrons coming out of fission right after the fission event. Like right after that nucleus has split into two, we get some neutrons that come out of the event. Technically, we give these neutrons a specific name, the ones that come right out of fission. Do y'all remember what those are called? Hmm. Yeah, prompt. The ones that come right out of fission are our prompt neutrons. And recall that this fission event happens like almost instantaneously. The release of these prompt neutrons happens almost instantaneously, like after the fission event. And these prompt neutrons are born. They come from these fission fragments, and these fission fragments are highly unstable. So they're very neutron rich, and that means that they're basically like almost immediately going to start decaying to get to a more stable configuration. And as these fission products are decaying and coming to a more stable configuration, some of them emit neutrons in the decay process. So the neutrons that come out seconds to minutes later after the fission event, as a result of these decays, so they are emitted due to these fission fragments and fission products being radioactive and beta decay. So they come from beta decay of our fission fragments. These fragments are very unstable. They are readily decaying. As they decay, some of them will emit neutrons in their decay process. And the decay, depending on the nuclide, it has a decay constant. Maybe it emits them in a second, maybe it emits them in a minute. There's kind of a variation to this. But the neutrons that come out later, we give them a name, and those are called delayed neutrons. The ones that come out of the decay of our fission fragments are called delayed neutrons. And so when we are doing reactor analysis and we're considering neutron production and loss, we have to make sure that we're accounting for the production of both prompt and delayed neutrons. And when a reactor is operating in a critical state, like a real reactor, it's going to be critical on prompt and delayed neutrons. So the accounting for delayed neutrons is very important. And today we're going to start to see how we can do that. Um, I want to talk just a bit about the physics of these delayed neutrons, like how they come about. Um, so what I want you to think about is this is showing a decay scheme of bromine 87, which is a possible fission fragment that can come out of fission. So, or sorry, it's a fission product. So you have a fission event. It produces arsenic 87. This thing that comes out of fission, it's going to be a fission fragment. It's going to be very highly unstable, and it's readily going to start decaying to get to a more stable configuration. So maybe 87 arsenic beta decays into 87 selenium, and then maybe 87 selenium beta decays into 87 bromine. And so this is a way that 87 bromine could make its way into our reactor. And 87 bromine is also radioactive. It's going to decay into krypton 87. But something interesting happens about 2.6% of the time. So about 2.6% of the decays go this way, and the other 97.4% of the decays go the other way. 97.4% of the time, bromine 87 emits a beta, produces krypton 87. Krypton 87 decays and produces a beta 2. But about 2.6% of the time, something interesting happens. And when bromine 87 beta decays, it beta decays into a metastable form of krypton 87. This metastable form is like has a little bit of extra excitation energy in its nucleus. And the way that krypton 87 stabilizes itself is it actually spits out a neutron to become a stable krypton 86. So this is an example of a neutron coming out of a delayed neutron coming out of a fission product. And the nuclides that produce these delayed neutrons, like bromine 87, they have their own name. They're called delayed neutron precursors. So this is an example of a delayed neutron precursor. And the delayed neutron precursors are just the isotopes that come out of the fission decay process that can decay and produce a neutron. So some of these precursors are going to come immediately after fission. Some of them are going to come from the decay of a fission fragment into a fission product. There's about 270 nuclides in total that are decayed neutron precursors. You don't have to know all of them. We really only care about like about a couple dozen of them are like of practical significance. They like emit neutrons in a time scale that's like significant to our reactor design. If something's emitting neutrons on a scale of like, days or weeks, like it's so small that we can ignore those. But the ones that are emitting neutrons on the scales of like seconds to a couple minutes are the ones that we really need to account for. So if we return back to our balance equation, this was our time-dependent, energy-dependent balance equation. This is like the most sophisticated way we could talk about neutron conservation in our class. And the only thing I've done differently that from what we've seen before is I just added a fixed source. And that's a perfectly valid thing to do. You kind of saw a simpler example of how you can add a fixed source like way back in, I think it was homework 2. This is a source that emits neutrons per unit volume, per unit energy, per unit time at a constant rate. So if this is our balance equation, then and this was set up without accounting for delayed neutrons, the way that we would account for delayed neutrons is well, if we are adding delayed neutrons, are those going to appear as like a production term or a loss term in our equation? There's going to be like an extra production term for those new delayed neutrons, because if delayed neutrons are coming into our system, that's a gain. And then we don't really have to change our losses, because like once a neutron comes into our system, we already have all the mechanisms to talk about what happens to those neutrons. Like, do they leak out? Do they have an interaction that removes them from the group? So we basically just need to add a delayed neutron source term. So that's what I'm going to say here is that we want to add a delayed neutron source term. And so we're going to keep that delayed neutron source term really simple for now. And we're just going to call it SDN as a function of E. So that's just the source of delayed neutrons. And that's just, it's a gain term. So it's an extra plus term on the right side of my equation. So with that new term added into our equation, the equation looks like this. This equation might look complicated, but don't let it scare you. It's just a conservation statement. All this equation says is that the rate of change, technically the way this is expressed is I moved all the loss terms on the left-hand side too. So technically it says rate of change plus my losses equals my gains, but this is just a conservation statement. And each of these terms in my equation has physical meaning and has units. When you write an energy dependent diffusion equation though, every one of these terms picks up per EV units. So each term in this equation is a rate, density, and energy. It's, or you could also think of it as an energy dependent rate density. So it has units of neutrons per unit volume, per unit time, and per unit energy. Um, so if we want to proceed, then we need an equation or several equations for that delayed neutron source. And we're going to define a couple terms. Ci is the density of type I precursors at some time t. So it's a density of those delayed neutron precursors. It has units of inverse centimeters cubed. Lambda I, that's the decay constant for those type I precursors. It's a decay constant, so it has units of inverse seconds, just like the decay constants we saw when we were doing decay chains. Chi sub I is the energy spectrum for neutrons coming out of decaying type I DNPs, or delayed neutron precursors. It has the same units as any fission spectrum would. It has units of 1 over EV. And so we can construct our delayed neutron source term using each of these individual quantities. Because notice, this delayed neutron source term is like a reaction rate per unit volume and per unit energy. And if I multiply these three quantities together, Ci times lambda I times chi I, that's actually going to give me the units that I want. But I'm going to have multiple delayed neutron precursors, so I would have to do these calculations for every precursor group that I have. So what this is going to look like is it's going to look like a summation from I equals 1 to the number of delayed neutron precursors. It's supposed to be a D. And what I'm summing is the product of a chi I of E times a lambda I times a ci of t. And notice that chi I has units of 1 over EV, lambda I has units of 1 over seconds, and Ci is a concentration. It has units of 1 over centimeters cubed, so that overall, this source has units of centimeters cubed per second per EV. So the units match up for what we were trying to represent as like an energy dependent delayed neutron source term. Um, this is all well and good, but it requires that we know those delayed neutron precursor densities. And so if we want to find those precursor densities, we need to develop an equation for that. And we can actually go to our favorite equation, conservation, to find a way to write the delayed neutron precursor density. So conservation, it's just going to say rate of change equals my gains minus my losses. In this case, the population that we are trying to do conservation on is our delayed neutron precursors. So we'll say our type I delayed neutron precursors. we're um, we're considering the gains of these delayed neutron precursors and the losses of these delayed neutron precursors. Um, if I know the decay rate, sorry, if I know the decay constant, how would I get the decay rate? Because that's going to be the loss, right? The gains are because delayed neutron precursors are born from fission. The losses is because they are radioactive and they decay. So how would we write a formula for like a loss rate due to decay? Didn't it look like when we were doing this with our decay chains, didn't it look like a lambda times an n? And so here, n, and when we were writing n, it was representing the atom density. So like particles per unit volume, number of particles per unit volume. So here, that's what the precursor density is doing. So the decay rate is just lambda I times Ci of T. So like hopefully we can see how that is very similar to how we talked about decay when we were doing decay chains. It's the same formula. It's a decay constant times the density. Um, so that's what our loss rate is going to look like. And then there's going to be a gain rate too. All of these precursors are coming from fission. So the production rate of these DNPs, these delayed neutron precursors, is also going to be tied to fission, right? Specifically, it's going to be tied to the fission rate density. The fission rate density. And we'll make a simplifying assumption, which is that every time a delayed neutron precursor is born, it produces exactly one delayed neutron. So each DNP that's formed produces exactly one delayed neutron. So if every single time a delayed neutron precursor is born, it produces one neutron, then we can introduce new D for group I, which is the number of delayed neutron precursors that are produced from a fission caused by a neutron with energy E. So this is how I can write the number of delayed neutrons. If nu di is the number of type I precursors being born from fission because of a neutron with energy E, and every one delayed neutron precursor produces one delayed neutron, then we can use this quantity as like our nu for delayed neutrons. It basically represents, if it's a one-to-one, then it is also equivalent as telling me the number of delayed neutrons that are produced from a type I delayed neutron precursor. And so if we have a nu and there's a flux in our reactor and there's also a sigma F in our reactor, then we can construct our the conservation equation for these precursors is going to say rate of change equals rate of gains minus rate of losses. So this is the rate of change, right? D by dt of the quantity we're trying to conserve. The gains are due to fissions producing these precursors. So the gain term is going to look like it's basically just going to look like our fission integral. We're integrating 0 to infinity dE prime of nu di as a function of E prime times our sigma F, which can depend on R and the incident neutron energy E prime, times the flux, which is a function of R and E prime. Oh, and then the flux, sorry, can also depend on time. Right? So that's the gain term. It looks just like a fission production term. And that's because all of the delayed neutrons are ultimately forming from fissions, and every one delayed neutron precursor produces exactly one delayed neutron. And so that was the gains, and then it's gains minus losses, and the loss was the decay of these precursors. And we already said that that was the equation for the loss. So this becomes our equation for the precursor densities. Oh, question?
the other two, for instance, sorry,
The nu and the sigma f.
yes.
Those do not have time dependence. Right now, we're not including any of our materials changing as a function of time. Yeah, so that's why there's no time component of those. So if we collect our equations together, now instead of having the SDN of E, we've replaced it with that summation. And then this summation depends on the precursor densities, and now we've developed an equation for those precursor densities. And this is a C subscript I, we would have a precursor equation for every neutron precursor we had. Like if we had 6 delayed neutron precursors, then we would have 6 equations here, C1, C2, C3, all the way up to C6. So notice that in this first equation, we have a scalar flux, and in this first equation, that whatever that scalar flux is, it's going to depend on this delayed neutron precursor term, which means that the flux is going to ultimately end up depending on what the precursor density is. So the scalar flux is going to depend on the precursor density. From equation 1, if we wanted to solve equation 1 for the flux, the precursor density is in there, so it's going to affect what my flux is. The density, the precursor density will affect my flux. But also, if I look at my second equation, the production of these precursors is also based on the flux. So the flux depends on the delayed neutron concentration, but the delayed neutron concentration also depends on the flux. So if we have 2 separate equations, each of them that have variables that are like I have I have 2 variables in one equation, I have these 2 variables in my other equation. What it basically means is that we have a system where the flux and the precursor concentrations are coupled. And I need to know both to be able to find either one. So this is a coupled system. Coupled system of equations. And if we have the right assumptions, we actually can solve these equations and get some analytical, do analytical calculations from these equations. So that's going to be our goal, is to next make some simplifying assumptions so that we could rewrite these equations in a form that is analytically solvable. But notice that what we're starting from is just a conservation statement. So if we're starting from a statement of conservation, whatever equations we develop, they're basically just going to be expressing conservation too. And ultimately what we're going to do is get a equation that will allow us to talk about the time dependence of this system. So that's where we're going. And to develop our equations, we are going to assume that we have an infinite and a homogeneous medium. So just going back real quick, if this is my equation, but if I say that the medium is homogeneous, how is that going to allow me to simplify how I'm writing the equation? Homogeneous means, what does homogeneous mean? So it means that if it was to the extent that we don't account for clouding, really what we would want to say is that as we go from place to place, the composition doesn't change, right? So that means that that means that if it's homogeneous, we don't have to write position arguments, right? Because nothing varies with position. And if the reactor is infinite, are there any of these terms that go away if we have an infinite reactor? In an infinite reactor, is there any leakage? No leakage, right? So that means that this term right here with the Laplacian would end up dividing, or would just become 0 if it was infinite. So going from that previous slide to this slide, I've already made those changes, right? There's no leakage term because it's infinite, and there's no position arguments on any of my terms because it's homogeneous and everything's the same. And so these are our equations. And the next thing that we are going to do is we've got an equation that's energy dependent, and we're just going to integrate over all energies so that we remove the energy dependence from our problem. So what this is showing is just what it would look like if I were to integrate every term with respect to energy. The only kind of funny business that you might see is on this first term right here. You have a time derivative of phi, but once you also integrate over energy, it's a thing where you're integrating over energy, you have a derivative with respect to time. Energy and time don't interfere with each other, so I can pull the time derivative out and I could put the energy integral in, and I'm not breaking any rules. So that's all that's been done on this term, is I've just rewritten it so that the time derivative is out and the energy integral is pulled in. Um, and every other term, I'm just writing it as an integral over all energies. And this is going to end up simplifying a lot because of our definitions for a lot of these terms, like chi-i and chi-prompt, and this scattering PDF, which is baked into my differential scattering cross-section. These are all probability density functions, and that means that if I integrate them over all neutron energies, what do they equal to? They all give me 1 if I integrate them over the neutron energy, over all neutron energies, because they're probability density functions. So when I do that, a bunch of terms end up just simplifying because of the fact that those probabilities are 1. And the next thing I'm going to do is I'm going to just replace. So in my equations, I have an E prime and I have an E in some of my terms because the fission and the scattering are due to a neutron with some energy E prime. The initial energy is E prime and the final energy is E. But once I've integrated over energy, the E is kind of like a dummy variable. And so I can just rewrite the E primes as E's. And then that's how I get to this equation. I make those PDFs go to 1 and I replace E prime. I just do a dummy variable swap from E prime to E. And then, oh, and I forgot to move this one, but so notice this term right here has a sigma t, and this term right here has a sigma s, and we're integrating over the same bounds. So I could subtract this scattering term from both sides, and then over here, I would have a sigma t minus a sigma s, which would give me a sigma a. So if I use that definition and I move the scattering integral to the left side, then that sigma t minus sigma s gives me this sigma a right here. And now that I'm here, I basically have a equation for the energy dependent flux. And what I want to do is, instead of writing it in terms of the flux, I want to write it in terms of the neutron density. So I want to write my flux as a function of the neutron density and also the speed, if possible. Do y'all remember how I could write the flux in terms of the neutron density and the neutron speed? Yeah. Oh, it's actually the other way. It's NV. Because N is like sorry, N is like my number density, right? N has units of like neutrons per centimeter cubed, and then V is like centimeters per second. So notice that if if, just to be precise, if I keep these as neutrons, then notice when I multiply N times V, don't I get a neutron path length rate per unit volume? So that was kind of like where we got that definition from. And that's what I want to substitute in here. So I'm going to say that it is a number density that could depend on E or T times a speed, and the speed is going to depend on the neutron's kinetic energy. So that's the fundamental relationship between my energy dependent flux and my energy dependent neutron density. And if I wanted to get the neutron density by itself, I would just divide both sides by V. So I would have phi of E and T over the speed of the neutron with energy E is my number density. And so what I am going to do is I'm going to rewrite the above equation in terms of the number density. So for example, notice that this right here Isn't that just equal to the number density? This quantity in the first integral? So this first term is going to be d by dt, integral from 0 to infinity, dE of n of E and t. Right? In that first term, phi over v is by definition n. So that's what that first term becomes. In the second term, I'm just going to replace the flux with its definition. So I'm going to have integral 0 to infinity dE sigma s of E times v of E times n of E and t. Then I've got my equal sign. Not going to do anything with the external source term, and not going to do anything with the delayed neutron precursor term. Oh, yes, I did. Thank you. I was testing you. And then the last term, I'm going to do something very similar. I'm just going to rewrite the fission term in terms of the number density and the speed. So that's going to look like integral 0 to infinity dE of a new fission prompt E sigma F of E, V of E, and N of E and T. And those are the three terms that I have like on the right-hand side. So hopefully that's not too bad, and we can see how we make those substitutions. And um, from there we can make some clever use of some definitions of terms that we've either defined before, or we can make some use of some averaging to rewrite the three terms that we just wrote here. So if that's okay, I wanted us to think about what these terms are, and I wanted us to recognize that like that first term, we're integrating the energy-dependent neutron density over all energies. So if the energy-dependent neutron density is like neutrons per unit volume per unit energy, and then I integrate that quantity over all energies, what am I going to get out of that integration? If I integrate the energy-dependent density over all energies, what do I get out of that? You just get the number density, right? So you just get the neutron density n of t. Absolutely. Because the integrating over all energies basically knocks out those per EV units. And so this is the neutron density now, and it just has units of neutrons per centimeter cubed. And we can make a similar argument about our external source, that if this is an external source with units of neutrons per unit volume and per unit energy, if I integrate that over all energies, I'm just going to get a total source term that talks about neutrons of all energies. So that is just going to give me some total source term, which also has units of neutrons per unit volume. So like n of t now represents the density of neutrons of all energies. Now that's what this S total represents. It represents the source emission per unit volume of neutrons of all energies coming out of my source. Question? Oh, so oh, you're right. Yes, sorry. The source, yes. This source does have per time units on the bottom. Because okay, so the SEXT, this was neutrons per unit volume, per unit time, and per unit energy. Technically, this term right here has a d by dt in front. So that's why, like, if I go to this equation, that n, the thing that's integrating this first term, which becomes n of t, it still has the d by dt up front. So overall, when I do d by dt of this and d by dt of that, I have units that give me neutrons per unit volume and per unit time. But yeah, this one does have those time time units baked in here. So when I do this integration, this term has units of neutrons per unit volume per unit time, where this is just neutrons per unit volume. And so with those other two terms, we're going to be clever about our use of the definition of an average. And so I've just rewritten the same thing two times because a thing can be equal to itself. And then what I'm going to do is I'm going to multiply the right side by something over itself. I'm going to multiply it by 1 in a clever way. So in here, what I'm going to multiply by is the integral from 0 to infinity of n of e and t dE. And I'm going to do this on the top and the bottom. I'm multiplying the top and bottom by that same integral. So I haven't changed anything because I'm just multiplying by 1. But now what I can do is I can recognize this is the definition. If I look at the numerator and then this denominator, if I look at that part in the blue, that looks like the definition of an average of the sigma A times the neutron speed. So what I have in the blue is the average of my neutron speed times my sigma A. And what's left over, that integral in the numerator, I'm integrating my energy dependent neutron density over all energies. And we just said that that's the same thing as n of t. So this whole term, this whole absorption term can be represented like this as an average v, average speed times sigma A times my number density. So that v times sigma A with the brackets, that's a weighted average of that quantity, the speed times the macro absorption cross-section, and it's weighted to the weight function, which is the neutron energy dependent density. So that's what that term becomes, and we can do a similar game with the, let me just make sure people are still, don't want to go too fast. But ultimately, we're gonna play a similar game with the fission term so that the fission integral can be rewritten in a similar way, and then we'll have all of the simplifying that we've needed to get to like this new form of our equation. Oh, sorry. So this V times sigma A, though, it's going to have units. And if we think about, I'm thinking about this term right here, what would be the units of V, of the speed? And then what would be the units of the absorption cross-section? 1/centimeters, perfect. So notice that this V, this average V times sigma A, those centimeters are going to cancel. So what I'm left over with is units of inverse seconds. This quantity V times sigma A average has units of inverse seconds. And so if that's all okay, then I'm going to do a similar game with the fission term. I'm going to take it and I'm going to also multiply it top and bottom by the integral of my energy dependent density. And then what this is going to give me is it's going to look like a weighted average of the speed times nu fp times sigma f and then times n of t. Where again, what we're saying is that the thing on the bottom and then this big integral, that's what gives me the definition of an average of those quantities. It's an average of those quantities weighted to the neutron energy dependent density. And then what's left over is the energy dependent density integrated over all energies, which just becomes n of t. So then if we plug all of those definitions into our conservation equation, now we have an equation that looks like this. And remember that we have written all of this for an infinite and homogeneous reactor. Now we're going to define two new terms. So we're going to define the delayed neutron fraction. The delayed neutron fraction. We use a symbol beta with an overbar for this. And as the name suggests, it's the fraction of fission neutrons that are born delayed. Fraction of fission neutrons that are born delayed. And so in terms of material properties, this V times nu Fp times sigma F, that's kind of like the production rate of fast neutrons, prompt neutrons. So the way that I would write this for the fraction is it's going to be the average of V times nu Fd, the number of delayed fission neutrons times sigma F, divided by the total, which would be V times nu, I'll just say nu F times sigma. So FD is the delayed number of neutrons emitted per fission that are emitted delayed. Nu FP is the number that are emitted per fission that are fast, or sorry, that are prompt. And F without an extra subscript is the total. So I guess by the definitions here, what I'm saying is that the total is nu F prompt plus nu F delayed. Right. Everything that's emitted prompt plus everything that's emitted delayed is what our total number is. And previously, we've just been using, whenever we've been writing nu F, we've just been kind of lumping everything together, prompt plus delayed. Now we can kind of be more explicit in how we write our equations. So we have terms that account for the prompt part and parts that account for the delayed part. And the delayed neutron fraction will allow us to do that. The other thing we need is this LP. This is defined as the average time from neutron birth to from prompt birth to absorption. So from prompt birth to absorption. And so it's an average time. And what this is actually going to look like, we are seeing how that V times the sigma A had units of inverse seconds. If we do 1 over that, that'll have a quantity that gives us units of time. And that's actually what this prompt neutron lifetime is. It's 1 over that average V times sigma A. So that's just the definition of what we call the prompt neutron lifetime. And it's a time, so it has units of seconds. Because V sigma A had units of inverse seconds. So if I do 1 over that, it's going to have units of seconds. From there, so what we're saying is that LP is also called the prompt neutron lifetime. That's the way that I remember it. Right? So it's a time in seconds that tells you about, on average, how long does the neutron live in the reactor. If it was born prompt, how long is it there before it gets absorbed? And then if we wanted to write K, this is an infinite, we assumed an infinite system. So how would we write K? Like, what would K infinity be? Do you remember what we said, what the formula for K infinity was? Perfect. Yeah, it was nu F sigma F over sigma A. So here, we're just expressing everything's with averages. So it's going to look like the average of V times nu F times sigma F divided by the average of V times sigma A. It's basically the same exact definition, but just to be consistent with the terms we've already defined, we're writing it in terms of the average fission production divided by absorption. and as opposed to the without the V and without the average. And from here, we're gonna introduce the definition of beta. And if we make that, if we introduce that quantity, we can rewrite this K so that it looks like it looks like V times nu F prompt times sigma F divided by 1 minus beta times the V average of V times sigma A. So that is how we can define K for an infinite medium in terms of the delayed neutron fraction beta. And the reason that we've done that is so that we can rewrite our balance equation using these new terms, using like beta and the prompt neutron lifetime and etc. So if we substitute n to our equation, we'll get this. And the next thing that we're going to do is in this term in the brackets here, we're going to divide top and bottom by V average of V sigma A. So when we do that on the top and bottom, these terms divide out. So if I look at what I have left in the numerator, when I divide top and bottom by V sigma A, here I just get 1 minus beta times K minus V sigma A. Sorry, minus 1, because I've divided this out on both sides. And then on the bottom, I've got 1 over average V sigma A. And by definition, the 1 over the average V sigma A is my prompt neutron lifetime LP. So I've made that substitution, then I've massaged the terms in the brackets by dividing out that V sigma A average. Then I've introduced that other definition of the prompt neutron lifetime. And then unfortunately, we have to define 2 more terms, but only 2 more, and then we'll be where we need to go. So last but not least, so if we essentially what we're going to do is just distribute this 1 minus beta into K. So if I go to the next slide, that's all I've done here. And then what I'm going to do is I'm basically going to divide top and bottom of this expression by K. And then I'm going to rewrite. So basically, I'm just going to do a couple algebra steps. And what I'm going to be left over is K minus 1 over K minus beta over the quantity LP over K. So to go from here to here, it's basically you're dividing top and bottom by K, and then you're rewriting the numerator. And we're rewriting it in this form with a K minus 1 over K on purpose because we have a new definition that we're going to introduce that is this K minus 1 over K. And that's actually how we define rho, which is the reactivity. So rho here is reactivity. And it is defined by definition as being K minus 1 over K. So we can hopefully see that we're going to make that substitution in right here. And then also in the denominator, we've got this LP over K, and we're going to introduce a new quantity called the mean generation time, and we use the symbol big lambda for that. So this is the mean generation time. And as a formula, that's by definition, it's just LP over K. And what that represents is the time in seconds that it takes for n neutrons to have n children. Notice that from this equation, we actually have a relationship between the mean generation time, the prompt lifetime, and the multiplication factor. And if we now throw these 2 definitions into here, that will be the last step that we need. So when I plug those definitions into here, this term in the brackets, it becomes rho minus beta over big lambda. So that's like our final form of the equation for the neutron density. And the only thing that we need to do is define, actually I lied, we have to define one more thing, and that's beta I. And beta I is basically the fraction of our neutrons that are born that are type I delayed. So we'll call this the fraction of fission neutrons that are type I delayed. So like conceptually, I would just think of that as like the fraction of my neutrons that are emitted delayed. And just coming out of type I precursors. So this would be V times nu di times sigma F over the total. So over V times nu F times sigma F. And if we introduce that definition, then we can write the standard form of the precursor concentration by substituting in this definition for beta I and also substituting in the definition for the mean generation time. So that was a lot of work to get to this final point, and that's we're at a good spot though. So essentially now we've got the equations that we can solve. And essentially these two equations are going to be it's going to be like the main focus of next class. Today we've developed the equations, and then next class we are going to see how we can use these equations to better understand how understand time dependence of our neutrons. And better understand the behavior of neutrons and reactors in problems where you have time dependence. So we have these equations, they have a special name, and these are called the point reactor kinetics equations. Point reactor kinetics equations. And how did we get these? Like, what did we start with? What kind of equation did we start with? Conservation, right? So these are just conservation equations. Fundamentally, that is what it represents. And you could actually plug in all of the definitions we introduced back into these things and go back to the place that we started from. The name is kind of misleading. They don't treat the reactor as a point. It really just assumes that there's no spatial variation in the reactor. And we've got all of these new quantities that we've defined, and a lot of interesting problems that we can solve. Those quantities are basically constants, and that's going to allow us to do analytical calculations to see how our systems evolve as a function of time. So that's going to be our goal moving forward, and that's what we're going to focus on next time. So this is enough to get you through about the first half of homework 5, and then what we cover on Tuesday will get you through the last half of homework 5. And I still have to think about after the exam week. I'm gonna try to get us back to the normal schedule after the exam week, but I think the next two are gonna be assigned on Thursday and due on Thursday. Yeah. So yeah, thank y'all for your time. If y'all have questions about the homework or anything else, I'll stay back a little since I don't have the help session this week. And if anybody wants more snacks, feel free to grab another one if you liked it. And yeah, if y'all don't have questions, then have a good one. Take care. Have a good 4th, and I'll talk to y'all soon.
So for problem 2, it gave us the extrapolated radius and the extrapolated height, right? And I thought I remember somewhere seeing that the extrapolated height is the regular height plus 2 times the thing.